Yes, good morning, students. In this class, I'm going to explain EMI. EMI means electromagnetic induction. By changing the magnetic field, electric field will be developed. That's called electromagnetic induction, inducing of the magnetic electric current by changing the magnetic field. Inducing of the magnetic field, inducing of the electric current by changing the magnetic field. First, we'll take what is a magnetic flux. The number of magnetic lines of force they are passing through unit area is called as the magnetic flux. Let us suppose it is the surface. This is taken as surface. For this surface, this magnetic field is like this. B bar is that magnetic field. Area of this one is taken as, this is the area. This full is taken as area. Okay. Then area is taken as it. It's a magnetic field. This is the magnetic field. Then if you draw a perpendicular to it, this is called as the normal, which makes an angle theta with this. B bar makes an angle theta with this n cap. Therefore, we take that magnetic flux phi is equal to B bar dot A bar. Magnetic flux phi is equal to B bar dot A bar. Magnetic flux phi is equal to B bar dot A bar. Otherwise, we may write flux phi is equal to BA cos theta. Flux phi is equal to BA cos theta we will take. Instead of this, if the surface is like this, and the magnetic field is perpendicular to that, magnetic field is perpendicular to the area. Angle between that area and this is a plane is taken as 90 degrees. That is, it is nothing but in the direction of the, it is in the direction of the normal. Normal also we are drawing in the same direction. This is the normal drawn. Magnetic field B bar and normal drawn, they are in the same direction. Angle between the magnetic field and the normal is taken as 0 degrees because magnetic field is along the direction of the normal. Therefore, we will take magnetic flux phi is equal to B A cos 0. B A cos 0. Then phi is equal to cos 0 becomes 1. B A into 1. Then magnetic flux phi is equal to B into A. We will take magnetic flux phi is equal to B into A. Right? This is a magnetic flux. Phi is equal to B into A. Next, if the magnetic field is along the direction of the plane, if the magnetic field is along the direction of the plane, this is that area. If the magnetic field is along the direction of the plane, means if it is like this, normal drawn is perpendicular to it. We have drawn the normal like this. Angle between the normal and the magnetic field we take. So this is n cap and this is a B bar. So this B bar is parallel to the surface. That means with the normal it makes 90 degrees. Therefore, magnetic flux phi is equal to BA cos 90. So cos 90 becomes 0. Flux phi is equal to BA into cos 90 becomes 0. BA into 0. then flux phi is equal to 0. Like this, we will write. Okay. So while we are inserting a bar magnet into the loop, when the current is flowing in a circular loop, let us suppose current is flowing in it. If the current flows in the circular loop in the anti-clockwise direction, current is flowing in this loop in the anti-clockwise direction, flow of current is there. So flow of current is there in anti-clockwise direction. So then this loop will act like a north pole. When the current is flowing in the circular loop in the anti-clockwise direction, then it will act as the loop will act as means this face of the loop will act as a north pole. If the current is flowing in the circular loop in the clockwise direction, if the current is flowing in the circular loop in the clockwise direction, then the flow of current will be. Then the flow of current is to be taken as this is clockwise. We'll say that clockwise. Current is flowing in the clockwise direction. In such case, if the current is flowing in the clockwise direction, that will say this face will act like a south pole. This face will act like a south pole. Fine. If we are inserting a bar magnet into a circular loop, let us suppose it's a circular loop. Into the circular loop, if we are inserting a bar magnet north pole, if we insert this north pole, what happens? This will allow that current in the clockwise direction. It will allow the current in the clockwise direction, north. So the effect of the north pole is like this. So whenever we are inserting, it will be like this. If we are taking away this bar, means a bar magnet from the loop, this is a circular loop. From the circular loop, if we are taking away this south pole of the magnet, this is a north, and this is south. If you are moving away from this coil, this loop will act like a south pole. Here it will act as a south pole. As we are moving, that effect of the south pole is there. South pole is in motion. So now this is an effect of the north pole, because the north pole is entering into it. So instead of that, whenever we take this is into this, if we are inserting the south pole, the effect of the south pole will be there. This is the south pole, this is the north pole. If we are inserting the south pole, this will act like the south pole. It will act as a south pole. Then current will flow in the clockwise direction. Instead of that, this is a current is flowing through it. Sorry, bar magnet, we are taking away from the loop. North pole and south poles are there. This is the south pole, and this is south pole, and this is the north pole. Then while we are moving away this, the effect of the north pole will be there. Current flow will be in anti-clockwise direction. Okay. So then magnetic flux phi is equal to what? Magnetic flux phi is equal to B bar dot A bar. I have written phi is equal to B bar dot A bar. Otherwise, we take that magnetic flux phi is equal to B bar dot A bar. Flux phi is equal to B bar dot A bar. Or flux phi is equal to BA cos theta, we have written. For a single turn, for n turns, we'll write that. So n means capital N I is to write. For n turns, then flux phi is equal to NBA cos NBA cos theta. NBA cos theta we will take for n number of turns. Fine. So there's a magnetic flux unit is taken as SI unit of the magnetic flux is taken as SI unit of magnetic flux is Weber. Weber is the SI unit. Then CGS unit is taken as a Maxwell. CGS unit is taken as Maxwell. So 1 Weber is equal to 10 power 8 Maxwell. 1 Weber is equal to 10 power 8 Maxwell. That will take. 1 Weber is equal to 10 power 8 Maxwell. Fine. So this magnetic flux that changes with the number of turns, or the magnetic flux that changes with the magnetic induction, or change in the magnetic induction, or due to the number of turns also, means due to that area of the coil also, magnetic flux that depends, and this angle between the magnetic field and the normal. Based on the angle between the normal and this magnetic field, based on the angle between the normal and this magnetic field, this magnetic flux will be changed. So we will write that magnetic flux that depends upon phi is equal to NBA cos theta. So this change in magnetic flux will be there due to all these number of turns, magnetic induction, area of surface, and angle, right? So whenever we take that Faraday's laws of electromagnetic induction, Faraday's laws. Whenever there is a change in magnetic flux in the circuit, so whenever there is a change in magnetic flux in the circuit, then there will be an induced EMF. If the change in magnetic field is there, that induces an EMF, and the induced EMF induces the current. So whenever there is a change in magnetic field, there will be an induced current. Induced EMF is nothing but induced current. This is one, and this will be there as long as the change that persists, means what remains the same. Let us suppose it is a coil called as the solenoid. For that we attach a galvanometer, G for galvanometer. While we are inserting a bar magnet into it, north pole if I insert it, what happens? This change in magnetic field will be there. The magnetic lines of force will be there around this magnet. These magnetic lines of force, they will break. The magnetic lines of force, they will break. So as a result, there is an induced EMF, and induced EMF induces the current. So Faraday's first law states that whenever there is a change in magnetic field, it induces an EMF, and that remains as long as the change takes place. The induced current will be continued. Inducing of current will be continued as long as the change in magnetic flux changes will be there. Next, the EMF of the induced EMF, the EMF of the induced EMF, or induced EMF is equal to minus d phi divided by dt. Induced EMF is equal to minus d phi by dt. See, from the Faraday's law, we may write that induced EMF E is equal to minus d phi divided by dt. Induced EMF E is equal to minus d phi divided by dt, we will write. So in the place of the phi, we may write the above one. In the place of phi, we'll write this. The above one we may write. Right. Then, so the induced EMF is equal to minus d by dt of phi is equal to what? NBA cos theta. NBA cos theta. So then induced EMF is equal to NBA cos theta. This changes may be with that magnetic field. Let us suppose the change in magnetic field is there due to which NBA is constant. NBA is constant, then d by dt of cos theta we may take. Means cos theta 2 minus cos theta 1. So induced EMF is equal to NBA into, we may write cos theta 2 minus cos theta 1. Cos theta 2 minus cos theta 1 divided by time period t, we may write. So time period t. Or we may write like this. It changes due to that change in magnetic field. Induced EMF is equal to minus NA cos theta into the magnetic field. It may be changed. So that will be B2 minus B1 divided by T. Otherwise, T2 minus T1 also we may write. So induced EMF is equal to minus NBA cos theta into B2 minus B1 divided by T2 minus T1. So then instead of this, we may write this E is equal to minus NA into cos theta into dB divided by dt. Like this also we may write. Or this change in magnetic field, it is due to the area of the surface also. E is equal to NB cos theta into A2 minus A1 divided by T2 minus T1 also we may write. Or it may be with the number of turns also. We may write induced EMF is equal to AB cos theta into N2 minus N1 divided by T2 minus T1 also we may write. T2 minus T1 also we may write. Otherwise, induced EMF is equal to minus ABN into cos theta 2 minus cos theta 1 divided by T2 minus T1. Okay, like this we may take. So let us suppose a bar mag means, okay, as we got it, as it is the induced EMF. Induced EMF is nothing but voltage or potential. EMF is nothing but potential or voltage. We will take that. So instead of this theta, we may take omega t also. Flux phi is equal to NBA cos omega t also we may write. Why? Angular velocity omega is equal to angular displacement divided by time period. So therefore, we will write that angular displacement theta is equal to omega into t. Angular displacement theta is equal to omega into t. Right? So that we may write. Induced current, we have to calculate. Induced current, I is equal to E divided by R. I is equal to E divided by R. So I is equal to 1 by R into. What is the E? E is equal to NBA cos theta. NBA cos theta that we will take. Induced EMF I is equal to E by R. Fine. Or I is equal to, instead of this we may write I is equal to 1 by R into delta phi divided by delta t. Delta phi divided by delta t also we may write. Then we know I is equal to Q divided by delta t we may write. Capital K has to write. I is equal to capital Q divided by delta T also we may write. So therefore, charge Q is equal to delta phi divided by R. charge Q is equal to delta I by R. How did I write? See, once again, I'll repeat this one. Induced EMF, we know. Induced EMF E is equal to minus d phi divided by dt. It's fine. Then magnetic flux phi is equal to NBA cos omega t. Omega t or theta, cos theta. Cos theta. If theta is equal to 0 degrees, magnetic flux phi is equal to NBA. NBA only will take it. Right. Then from that a definition of the electric current, I is equal to Q divided by delta T, we may write. And electric current I is equal to E divided by R also we may write. E divided by R. E for d phi by dt. So I is equal to what? Minus d phi divided by R into a dt we may write. Right? Then I is equal to delta Q. It's nothing but dq I has to write. Q divided by dt. Q divided by dt. So Q divided by dt is equal to minus d phi by dt into R. So both sides dt get cancelled. Therefore, Q is equal to minus 1 by R into d phi. Otherwise, Q is equal to magnitude whenever we take that d phi divided by R. 1 by R into d phi we may write. Like this we may write. Okay. Then whenever we are dropping a bar magnet into a circular loop or circular ring. This is the circular ring. While we are dropping that bar magnet freely, let us suppose this is the north pole, this is the south pole of the bar magnet. We are dropping into this, let us suppose this is a bangle. So while we are dropping in the downward direction, acceleration is less than that of the acceleration due to gravity. Generally, if it is not magnet and any object, if it is dropped, or magnet also, if it is dropped directly without this ring, that is acceleration. It will move with the acceleration equal to acceleration due to gravity. But when we are dropping this into a circular ring, what happens whenever the bar magnet that enters into circular ring, the effect of the north pole is there. This loop will act as a north pole. So as the north pole we are moving towards this circular loop, this face will act as a north pole. Some opposition will be there on it. Some opposing forces will be there on it. That's why acceleration of this bar magnet is less than that of the acceleration due to gravity. Once again, I'll repeat. Whenever we are dropping a bar magnet, into a circular loop, then acceleration of this bar magnet will be less than the acceleration due to gravity, because this bar magnet, whenever it is dropped, this loop will act like a north pole, and the effect of the north pole will be there. North pole and north pole, they repel one another. That's why some opposition will be there for this magnet, on this magnet due to the loop. Okay, that is acceleration. So then whenever we take that, net acceleration is equal to net acceleration is less than acceleration due to gravity in this case. Okay, it falls down. It is coming from the loop. If we have dropped, it is coming from the loop. This is the loop. So if the bar magnet that is coming from this loop downwards, I have taken. Now also this is called as the south pole, this is the north pole. So then what happens? The effect of the north pole will be there. This is the effect of the north pole will be there. When the bar magnet is moving like this, the effect of the north pole will be there, and again this loop will act as a north pole. This loop will act as a north pole, and the anti-clockwise direction flow of current will be there. Flow of current will be there in the anti-clockwise direction. In the anti-clockwise direction. So in this case also, acceleration is less than acceleration due to gravity. Fine. Next. When we are rotating a rod of length L, let us suppose a rod in the uniform magnetic field. In the uniform magnetic field, this into represents the inward magnetic field. In the uniform magnetic field, while we are moving a rod of length L, if we are rotating the rod of length L in this uniform magnetic field, a rod of length L is there, length of the rod is taken as L. This rod we are rotating, this rod of length L is there, this we are rotating in this uniform magnetic field. If we are rotating this uniform magnetic field, then induced EMF E is equal to that strength of the magnetic field is taken as B, and the velocity of this rotation is taken as B. Length of the rod is taken as L. About the point O, we are rotating this rod of length L. So induced EMF E is equal to B into B bar into we'll write that L bar cross V bar, we may write L bar cross B bar, we may write. So then if we are rotating this rod with angular velocity omega, then we'll take that induced EMF E is equal to 1/2 B L square omega, 1/2 B L square omega. So then when we change that magnetic field in a coil, if we are changing that magnetic field in a coil, then induced current also will be there in that coil. Such concept will say that self-inductance. Self-inductance means whenever there is a change in magnetic field in a coil, self-inductance, whenever there is a change in magnetic field in a coil, that induces EMF in that same coil. If the coil is taken, if this is a coil, if the change in magnetic field is there in that coil, and induced EMF also will be there in that coil. So that we call as the self-inductance. So phi is proportional to I. Phi is proportional to I, or phi is equal to Li. Phi is equal to Li. Then L is called as the coefficient of the self-inductance. So L is equal to phi divided by I, we will take that. So therefore induced EMF E is equal to minus d phi divided by dt. Induced EMF E is equal to minus d phi by dt. Otherwise E is equal to minus L into di divided by dt, because phi is equal to what? Li. Phi is equal to Li. So E is equal to minus L into di by dt. Once again I'll repeat. Whenever there is a change in magnetic field in a coil that induces EMF in that coil, it's called as self-induction. Phi is proportional to I. Change in magnetic field is directly proportional to induced current. Then to replace the proportionality, we multiply with a constant. Phi is equal to Li. Then according to Faraday's laws of electromagnetic induction, induced EMF E is equal to minus d phi divided by dt. Minus d phi divided by dt. So E is equal to minus d by dt of phi is equal to what? Li. Then E is equal to minus L into di divided by dt, minus L into di divided by dt. This is self-inductance is given like this. So mutual inductance. What is a mutual inductance? If the change in magnetic field is there in one coil, and induced EMF if it is there in the other coil, that is called as the mutual inductance. This is called as the primary coil. This is called as the secondary coil. If there is a change in magnetic field in the primary coil, then induced EMF will be there in the secondary coil. So phi S is proportional to IP. That means whenever the change in magnetic field is there in the secondary coil, that induces the current in the primary coil. So phi S is proportional to IP. Therefore, phi S is equal to M into IP we will write, where M is called as the coefficient of the mutual inductance. Then we write M is equal to phi S divided by IP, that we may write. So from this, induced EMF is given by induced EMF E is equal to minus d by dt of phi. So in the place of phi, we will write minus d by dt of phi is equal to M into IP. That is, E is equal to minus M into d by dt of IP. D by dt of IP. Like this, di. This is induced EMF E is equal to minus M into di by dt we will write. These are the formulas, right? This is a very small chapter. See, in electromagnetic induction, induced EMF in a coil is independent. So induced EMF in a coil is independent. Induced EMF E is equal to d by dt of E is equal to minus d by dt of NBA cos theta. It will depend on these factors. So electromagnetic induction, the induced EMF in a coil is independent. So it depends upon the flux, it is correct. It depends upon the time period, correct, and resistance of the circuit, and none of the above. So it is induced EMF in a coil is independent on resistance. That's why which option is correct? C option is correct. So then is given that an electromagnetic induction, the induced EMF in a coil is independent on resistance of the circuit. It is independent on resistance of the circuit. C option is correct for this. The induced EMF is independent on resistance of the circuit. Induced EMF. Why induced EMF E is equal to, what did I write? E is equal to minus d by dt of NBA cos theta. This is right. Next one. Lenz's law is a consequence of law of conservation of. Lenz's law is a consequence of law of conservation of energy. Lenz's law that opposes the change caused by it. Whenever there is a induced EMF, that induced EMF will be opposed by the change caused it. Means what? Which changes that after inducing EMF, it opposes it. The change what it is caused by it, it will oppose it. So Lenz's law is a consequence of law of conservation of energy. Next, in electromagnetic induction, the induced charge in a coil is independent. In an electromagnetic induction, induced charge. I have written that formula for the induced charge. What is the induced charge? Induced charge Q is equal to delta phi divided by R. What did I write? Q is equal to 1 by R into, instead of delta phi, I have written d phi, no problem. So induced charge Q is equal to 1 by R into delta phi. 1 by R into delta phi. This is the induced charge. So induced charge in electromagnetic induction, induced charge in a coil is independent. Induced charge in a coil is independent on time. Why time? Already it is cancelled. What is that? Induced charge Q is equal to 1 by R into delta phi. That means it is independent on the time. Time factor is cancelled. Why? I is equal to E divided by R we used to write. So I is equal to Q by delta T is equal to E means what? Minus d phi divided by dt. This is also I'll write dt. So this dt into 1 by R. 1 by R into, once again I'll rewrite it. I is equal to Q by T we used to write. I is equal to Q divided by dt we may write. Is equal to 1 by R into, what is that induced EMF? E is equal to minus d phi divided by dt we will take. So both sides will cancel dt. That's why in electromagnetic induction, the induced charge in the coil is independent on time. As the time is considered cancelled, so Q is equal to 1 by R into d phi R delta phi we will get. That's why it is independent on time. B is correct. Next, the magnetic flux through a circular circuit resistance capital R changes by an amount delta phi in time period delta t. Then the total quantity of the electric charge is Q, which passing through this time through any point of the circuit is given by. Just I have explained you that the expression, the relation between that charge and the electric flux. Phi is charge Q is equal to delta phi divided by R. They have asked a direct formula. Q is equal delta phi divided by R. Next one. A cylindrical bar magnet is kept along the axis of a circular coil. The magnet is rotated about its axis. Then a cylindrical bar magnet is kept along the axis of a circular coil. And a cylindrical bar magnet is placed along the axis of a circular coil. If the magnet is rotated about its own axis. See, how did they say? Its own axis means it is that coil. It is that circular coil. And a bar magnet we used to keep like this. A bar magnet is to keep like this. Otherwise, about its own axis means what? This is like this. A bar magnet. This is the north pole and the south poles. I am going to mark. This is the north pole and south pole. If you rotate the bar magnet like this, if you move like this or move like this, effect will be there. Instead of that, if you rotate the bar magnet about its own axis, then there is no induced EMF. Induced EMF will not be there. There will be no induced EMF or induced current in the coil. There is no induced EMF or induced current in the coil, because we have to move this. We have to move this like this, or we have to move away from the coil. So instead of that, what we are doing, we are rotating about its own axis. Like this, we are rotating. That means what? We are rotating like this. We are rotating like this. That's why there is no induced current or an induced EMF. Next. The current is given as, the current in the coil of the inductance is given as 0.2. The current in a coil of inductance is given, L is equal to 0.2 Henry. Changes from I1 is equal to 5 amperes to I2 is equal to 2 amperes in the time period. In the time period delta t dt is equal to 0.5 seconds. Then the magnitude of the average induced EMF. What is the magnitude of the average induced EMF they have asked? So then induced EMF E is equal to minus L. So it's simply L into delta I divided by di by dt, delta not di by dt. E is equal to induced EMF E is equal to L into di by dt. Induced EMF E is equal to L into di divided by dt. L into di divided by dt. So induced EMF E is equal to L is how much? 0.2. Otherwise we'll write this 0 L into di means what? Di means I2 minus I1. We used to write that I2 minus I1 divided by time period delta t dt we used to write. So E is equal to L is 0.2. I'll substitute with a different color. Then d by dt. So then E is equal to L is 0.2 into I2 is 2 amperes, I1 is 5 amperes. 5 amperes to 2 amperes changes from 5 amperes to 2 amperes. Then we have to take difference only. We'll take that difference, delta I is to take. Di. So di is equal to 5 minus 2. That is equal to 3 amperes. Then I'll write here 3 divided by dt is equal to how much? 0.5 seconds. Therefore, E is equal to 0.2 divided by 0.5. It will be 2 by 5. 2 by 5 into 3. That will be 6 divided by 5. That will be equal to 6 divided by 5. 6 divided by 5, how much it will be there? 6. One time it get cancelled. 1 is there. 1.2. 1.2. This will be equal to 1.2 volts. D option is correct. 1.2 volt. Next. A rod of length. A rod of length L 2 meters is slides with a speed of 5 meters per second on a rectangular conducting frame as shown. That diagram, I didn't keep it as shown. I have to keep the diagram. So then consider the situation given in the figure. This is also a diagram I didn't keep. Okay. The magnetic flux linked with a coil varies as a function. Magnetic flux phi is equal to 3t square plus 4t plus 5 plus 9. So that magnetic flux phi is equal to 3t square plus 4t plus 9. Then if I take this d phi divided by dt, d phi by dt is equal to d by dt of 3t square plus 4t plus 9. So d phi by dt is equal to induced emf E. E is equal to 3 d by dt of t square, 3 into 2t plus 4 plus 0. So induced emf E is equal to 2 3s are 6, 60 plus 4. They have asked at time period t is equal to 2 seconds. T is equal to 2 seconds. We have to write E is equal to 6 into 2 plus 4. 6 into 2 plus 4. 12 plus 4. Okay, E is equal to 6 into 2. 6 into 2 will be 12. 12 plus 4. So induced EMF E is equal to 16 volt. B option is correct. Okay, this is I had other class. I have to attend for other class. Little bit late they have started. We'll see that rest of the things on Monday class. Right? I'm going to stop the class here.
Thank you, sir.
Thank you.